who I greatly admired and also enjoyed as a person. I should start by, the only thing I'm going to say of an anecdotal nature is my first encounter with John Bell, which had to do with a series of conferences. I think it was the first one on quantum gravity, which Dennis Sharma and Chris Isham and I organized. There were 3 of them eventually. I think it was the first one, but I'm not quite sure. I remember we were worried about quantum mechanics and certain aspects of the Copenhagen interpretation and so on, which we never felt very happy with. And we needed somebody, we felt, who would be able to express the conventional Copenhagen-ish view. Now, knowing very little about John Bell, except his theorem, which seemed to be establishing, showing that quantum mechanics was right. So we needed somebody to put the position, showing quantum mechanics was right. So we invited John Bell, and we were shocked and delighted to find that he really shared most of our views and was, I think he was, as far as I can remember at the time, he was thinking that, he probably was also a little bit under the misapprehension of what cosmologists thought, namely that they all liked the many worlds interpretation, which was certainly not what either the 3 of us wanted, but nevertheless, I think his talk was somewhat aimed at that. But I've forgotten exactly what he said, but I remember it was a very realist point of view, so that was very much the kind of thing. You see, that's reality here. Reality, I think the fact that he had this view of wanting to make sense of what we see and what's going on in the world and square that with quantum mechanics was something which we very shared, a viewpoint we very much shared with him. The non-locality, of course, was what he effectively established, and this is something which I don't remember it featuring quite that strongly in the. This was at a time, of course, when it was before GRW, and at a time when the Bohmian thing was, I think, was what he was plugging very much, I think, at that time, because it was giving us a way we can actually look at quantum mechanics in a way which gives you a sort of real picture of the world, which was very satisfying from our point of view. I don't remember ever talking with him about twistors, so that's specifically not very much to do with John Bell, but I'll say that what I want to say about twistors, namely how it relates to quantum non-locality, is of course very much a John Bell thing. I'm afraid that most of my talk will be about twistors, so I'll have to explain twistor theory because I'm not going to assume that people here are experts or necessarily know anything about the subject at all. So I'll have to say about twistors, and I'll go rather quickly, but I'm not expecting people to follow all the detailed equations and things like that. It's more the general ideas and the geometrical pictures and things which I want to convey. So, twistor theory, well, the pictures here give you the central idea. I have to stand in 2 places at once, it's slightly awkward. As you can see from the nature of the transparency, this is a pretty old slide, but I think it serves its purpose very well. Here we have a picture of space-time. This is Minkowski space, flat space-time. And I want to try and convey partly that twistors are about real things. When I was talking about 4-dimensional space-time, I'm not going to any high dimension in that respect. In fact, it's very geared to 3 space and 1 time. So 3 space very specifically, 1 time very specifically. So it's quite unlike things like string theory where you bring in extra spatial dimensions. It is primarily a transcription from a space-time picture to another picture. And this is meant to be completely equivalent. Now, despite being equivalent, you find that the things which are easy or natural to do in one picture tend to be obscure and a little bit complicated in the other picture. And that happens both ways around. So there are things which are nice and easy to do over here, which are not so easy over here, and vice versa, things which are easy and direct over here, which are a little bit obscure and hard to see what's going on down here. But it is a translation, it's a correspondence, a very specific mathematical correspondence. Roughly speaking, light rays, thinking of a light ray here, is represented by a point in the other space, And a point in Minkowski space, you think of all the light rays through it, and that is basically the celestial sphere. So here we have a point, and we're looking back along the light cone, and all the light rays through that point. That collection of light rays represents the point. And that collection of light rays will be a sphere, that is the celestial sphere. And one of the important points about the sphere that represents the point in space-time is that it is naturally, in some sense, a Riemann sphere. Now, when I say a Riemann sphere, I mean the complex plane with a point added at infinity. So it's a complex one-dimensional space, the simplest kind, which is topologically a sphere. And one of the remarkable features of this, which is very direct, is that if you think of here we're looking back at the past light cone, and we have two observers moving at great speed with respect to each other, and because of aberration, they will see a slightly different arrangement of the stars in the sky. But this arrangement of stars in the sky has this very important property that it is conformal. It actually sends circles to circles. So if you found a set of stars which seem to lie on a circle, then they will also seem to lie in a circle for the other observer. And it's telling you that you have a conformal picture of the sky. Okay, so that's a crucial thing. I've got three words written down here, all of which are important. The first word, complex. So this part, when I say this is a Riemann sphere, that is a complex manifold. And that's the simplest complex manifold. It's a complex curve. And so the idea is to think of this as a complex space. And the hope would be to think of the whole space, in some sense, as a complex space. And one of the reasons for thinking that's a good idea is quantum mechanics, because, of course, quantum mechanics is based on the complex numbers, the complex amplitudes. And so that was one of the ideas here, is to try and bring in a relationship with quantum mechanics. It's also non-local, and of course that's very important here in our conference. In fact, the scheme of Twistor theory came about before the famous Bell paper and all this, but nevertheless, I was already fairly persuaded that we needed some description of space-time which was in some important way non-local. It's not sort of clearly non-local after what Bell showed us, that we really do have to think of space-time or what's going on in physics as in some sense non-local, and I think that's very important. But I was already thinking that we needed some kind of non-local description. And mathematical sophisticated wasn't something that was an intention, but it turns out this way. So you have to worry about certain fairly sophisticated mathematical ideas, and one of these particularly will be the crucial point which I want to make in this talk. Now, you see, it's non-local in a rather trivial way originally, which is that we're talking about an entire light ray as represented by a point. So in a certain sense, the whole light ray is simultaneous. Well, of course it is, in a sense. If you were a photon traveling along, you wouldn't experience the passage of time, and so the whole thing, if you like, is a simultaneous entity. And in that sense, one is collapsing down the light ray to a single point, and it's encompassing some aspect of non-locality in doing that. But I'm saying that is a relatively trivial aspect of non-locality. Certainly doesn't involve any of the subtleties that Bell's theorem does in showing that quantum mechanics is fundamentally non-local. Now, the other aspect of the Riemann sphere, which this is very much to do with, is, of course, the amplitudes. We have particularly with spin half particle, you see it very clearly, and the combinations of up and down give you all the other directions in space. And this is a feature of the three-dimensionality of space. It works much more. The amplitudes have this very close relationship to directions in space, which you see through the behavior of spin half in particular, also for higher spin, but it's a little bit more complicated, and I won't go into that here. But you see again a Riemann sphere. We're looking at these complex numbers where they are allowed also to be infinite, because it's the ratio of the complex numbers that's important, and that is a Riemann sphere. And the geometry is very clear also, because here we have the complex plane, the green one here, and the complex numbers in there, or the vessel plane. And here we have the unit circle, and I put the Riemann sphere to have that unit circle as its equator, and by organizing things so your coordinates are fitted in the right way and so on. Infinity, of course, corresponds to when W equals 0, so that corresponds to the spin down, and that's the point down here. Any other spin will correspond to a point on the sphere. You just look at the ratio Z over W, put that on the complex plane, project from the south pole, and you get a point on the sphere. This is a stereographic projection, and the direction out from the origin gives you this direction of spin that corresponds to. So this is just sort of straightforward geometry, showing you the relationship between the geometry of three-dimensional space related to the amplitudes of the complex amplitudes of quantum mechanics. And that's really struck me very much for a long time, that you have inbuilt, in some sense, a relationship between geometry and the complex amplitudes. So part of the philosophy here is trying to make that complex geometry, which seems also mysterious and everything, and make it much more down to earth, or if you like, real. That's part of the reality picture. These are part of two-spinner calculus, of course, and these amplitudes here fit together to make a Weyl spinner, or a two-component spinner. And you can have an index like this, and that's the general idea. You can make that a little bit more geometrical by taking the direction to be along the light cone. The spinner corresponds to a direction along the light cone, and there is the phase of the spinner also is given by a flag plane through that direction, which can be an arrow on the section through the light cone here. I'm not going to worry too much about that. I just want to show that, as I like to do, these things which seem sort of mysterious and algebraic and you're not quite sure what they mean, very often do have absolutely clear-cut representations in ordinary geometry. And to make this clear is something I've always liked to do. What about twistors then? Well, if we have these two-component spinners, you can see a twistor, in a sense, is a pair of two-component spinners, and the most clear-cut connection between these and the geometry of a light ray are the following. This is all quite formal. I'll do it a little bit more specifically in a minute. That if you take the spinner pi, I'm calling them omega and pi because pi has to do with momentum, and you usually lose the letter p for momentum. So if you take pi times its complex conjugate, this is an outer product, no contractions, then that is essentially the momentum, and it's a null vector because this is an outer product. And omega has to do with angular momentum, which is omega is a letter often used for angular momentum. So here we have the picture. Here is our light ray, and here is an origin, and then pi has to do with the direction of that light ray, and omega has to do with the direction out from the origin intersecting the light ray. You'll notice I have this little helix running along the light ray. That is to indicate that there is something a little bit more than a light ray in the twistor, which I'll come to in a minute, which has to do with the angular momentum of if it was a photon, it would be the angular momentum of a photon. I want to make this point right early on, that I don't mean that the light ray is a photon. It's like saying, if you have normal description in space of particles, you would say a particle is located at a point. The point is not necessarily a particle, because there are lots of points in the space which don't have particles on them. So in the same way, the twistor is not a light ray. It's where the light ray could be, if you like. So thinking of it as the analog of a point in space, it's the analog in a different kind of geometry. You could say that particular photon, if it could be viewed classically, it would be perhaps represented by that particular twistor. But the twistor doesn't have anything to do with being a photon or any other particular massless particle. But the helix, or the twist, going along the light ray, is just to indicate that it's also got a spin, and the spin will be in the direction or either positively related to the momentum or negatively. So this can go one way or the other, and it could have a certain size too. So I'll come back to that. The angular momentum is actually a combination of omega pi bar and omega bar pi. You have to bring the pi in together with the angular momentum, with the omega, to get the angular momentum. I'll give you some formulae in just a minute, but I think the main thing is not to worry about the detailed formulae, but just to get the general picture of what I'm trying to say. So here we have initially, again, the same correspondence, just what I was saying a minute ago. I regard this as a sort of first approximation to the twistor geometry. To get a better picture of it, you see, I said this wanted to be a complex manifold here. One of the obstructions to this is almost immediate, namely that think of light rays and you count how many dimensions there are. It's a 5-dimensional space. Now, a 5-dimensional space is certainly not going to be a complex space because it's got an even number of dimensions. So can't be quite that. So what you do find is something a little bit more than that. This original picture here is just that subspace here. I'm calling that PN. That means projective null twistors. And that's this space. This space we just had is that one. Now here I drew the Riemann sphere as a sphere. I'll tend to draw it often as a line because it really is a projective line, complex projective line, which is a sphere. But I can't very easily. I might draw it as a long sausage sometimes to show that it's both a line and a sphere at the same time. This space then is a complex manifold. It's in fact a complex projective 3-space. We have coordinates for that space will be these things z. I'll have z0, z1, z2, and z3. And it's the ratios between these, since it's a projective space, the 3 independent ratios which give you the point in this space. And here I have the blue point here representing a light ray. Also you can have points up here and down here. So I've extended this 5-dimensional submanifold to a 6-dimensional complex projective 3-space. So it's 2 dimensions for each 2 real dimensions for each complex dimension. So it's a 6-dimensional as a real space.
Why does it have 4 coordinates then?
Because it's the ratios. It's the independent ratios of those 4 coordinates. If you want to describe a projective space, you take coordinates and then you're just looking at the ratios.
I understand.
Yeah. Now, what is the correspondence between these two pictures? The correspondence is what I call incidence. So incidence here means that the point lies on the line here. It also means that this point this line passes through that point. That's what it means. This gives you the correspondence between the two. Over here, the points are the blue things, and those are the ratios between the z's. And incidence is just this equation here. So here we have the Minkowski coordinates. R0 is the time, 1, 2, 3. And then you make this Pauli matrix sort of thing, and put an I in front of it, and the square root of 2 just to make things work nicely. And incidence means these two coordinates are this matrix times the other two. And the equation of Pn, that's this thing in the middle, is this Hermitian form. It's a mixed split signature, 2 pluses, 2 minuses, if you make this diagonal, which is written down explicitly there. So that is the space of light rays is represented that way, and extended into 2 halves by when you violate this condition here. So this is the equation of Pn, and this is the incidence relation. Okay, so that gives you the whole picture, but I want to relate this a bit more to the notation, index notation, and if you're not used to this index notation, I would say don't worry too much, because I'm not going to worry about the details of the formulae. I just want to tell you, but just to say what you mean, in the 2-component, van der Waerden notation, the spinors indices, which are capital letters, represent you take the tensor indices. Each tensor index is the product of a spinor index and the complex conjugate. I've got a prime on it when it's the complex conjugate. And you have this relationship which is explicitly written here, and you just take it for granted afterwards. And then this is the matrix I had before, and the metric is just epsilons. These epsilons are skew symmetrical objects. Don't worry too much about the details. This is the interpretation I gave you before at the bottom, because I'll just flash the formulae at you without expecting you to check any of them. Here we have the incidence relation again, written down. This is just the same as I had before in the other transparency. In indices, it's that. And here we have the twistor is the omega and the pi. The omega is the first two components, the pi is the second two, and the incidence relation is omega equals I r pi. And that's the important thing which tells you the relationship between the space-time given by the r's and the twistors given by the omegas and pi's. If you move the origin, the omegas change, the pi's don't. The complex conjugate of a twistor, you take the complex conjugate of each bit and swap them around. So this then gives you z bar, the scale, the norm, if you like, of the twistor, which is this equation of Pn. If this is 0, that is the equation of Pn. Generally, the interpretation is that you have a 4 momentum, which is along the light cone, which is null, points into the future. That's automatically, that comes about from the momentum equals the, I'm using abstract indices here, so I don't have a way of, people tend to write sigmas in there, but you don't really need the sigmas. If you get the idea of the abstract indices, don't worry too much about it. So the momentum is the pi times pi bar, as I said before. The angular momentum is this slightly more complicated expression with skew brackets and so on. Let's not worry about the details. The helicity, you see, a self-respecting massless particle ought to have the property that its angular momentum, when skewed with its momentum and dualed, is proportional to its momentum. So this is a condition. The Pauli-Lubansky spin vector, which is this thing, has to be proportional to the momentum. And the factor of proportionality is this thing S, which is the helicity. The helicity is a real number. It could be positive or negative, depending on whether it's right-handed or left-handed. And that is basically the norm. So when S is 0, that is the correspondence we had before. When S is not 0, that extends the correspondence to the top and bottom halves. So that's really, when the helicity is 0, we're talking about light rays. When the helicity is not 0, you're allowed to go up and down. So these points are really representing the angular momentum and momentum of a massless, a classical massless particle, according to relativity. And that's exactly what one's doing here. So that's, yes, wave functions. If you want to write down a twistor wave function, you might say, well, this is like P in X. Yeah, I can make a choice. Do I use position space or momentum space? Well, here it means, do I use the twistor space or the dual twistor space? Yeah, you can make a choice. Let's just arbitrarily say use the twistor space. That means if I have a wave function, or the twistor analog of a wave function, I shall be looking at a function of the z's, which is independent of z bars. Now, what does it mean to say it's independent of z bar? Well, it means you write down the Cauchy-Riemann equations, which are derivative of f with respect to z bar is naught. What does that mean? That means it's holomorphic, complex analytic. So to say you're independent of z bar means you are talking about holomorphic, complex analytic functions. Okay. Now, what about helicity eigenstates? Well, you look at what the helicity operator is. That is basically the Euler operator, dz d by dz. Displaced a bit, never mind about that. But the S operator, the helicity, is the Euler homogeneity operator, a bit displaced. The relationship between the homogeneity, which is n, and the helicity is given by this formula here, somewhere. Here, there it is. I sometimes have an H cross, sometimes I don't. If you ever see one, put it equal to 1. Sometimes the slides I'm using will not put it equal to 1, sometimes they will. But if you put your H bar equal to 1 every time, then you have a consistent picture. So we have the degree of homogeneity is twice this, is basically twice the, I'm sorry, no, n is twice the helicity, and minus 2 minus n is the degree of homogeneity. Okay. So if you want a twistor wave function, you look for a homogeneous, holomorphic function of z. You could use z bar, which you could rename as w, which is a dual twistor, and that gives you the dual representation. But you can use one or the other.
Are we only in a one-particle picture?
Yeah, for the moment, yes. But of course, you can handle many particles, but which of course one wants to do if one wants to talk about Bell inequalities and so on. I'll come to some of that in a minute. But let's talk about one particle for the moment. And we have wave functions. And these, I'm saying, could be any helicity. Of course, we only know about photons and neutrinos had they been massless. Gravitons, spin 1 instead of spin 2 instead of spin 1. That's okay if you like. When I say graviton, I mean a linearized graviton here. The relationship between the equations are basically these things, basically due to Dirac, actually, these higher spin fields. And you have the simplest thing you can possibly write down. And I should, before going further, I should explain the connection between the more normal way of writing gravitational or electromagnetic fields. You see, if you have a thing with two indices, symmetric, then there is this relationship between the spinor and the Maxwell field. If this is to be a real field, these two things will be complex conjugates. If it's a wave function, well, then one will tell you the left-handed and the other the right-handed part of the wave function of the photon. So this F is the photon, and the C, that's the Weyl curvature, linearized Weyl curvature in flat space, and that's related to a 4-index object. And these, in the case of the Maxwell equations, they just become this equation with two indices. In the case of the linearized gravitational field, it's this equation with 4 indices. So these things are already, you're talking about all the different spins, all in one equation, if you like. The connection between the homogeneities and the different particles is given here. The photon, the left-handed photon has has -4. The right-handed photon has +1 here, -4 homogeneity, and the left-handed one is 0 homogeneity. For the graviton, it's -6 for the right-handed one and +2 for the left-handed one. You notice this is hugely chiral, which is a curious feature of twistor theory. It is hugely chiral. If you want to hugely chiral, that is to say, it's handed. It's chiral. It's handed. Yeah. I don't know what. Yes, chiral. Yes, chiral. Yes. So if you reflect in the mirror, you go over to the dual twistor representation, but you have to make a choice. So you say, shall we use the twistors or the dual? And once you've chosen one or the other, you've chosen the chirality. And this is reflected in the rather strange different homogeneities you have here. In the linear case, it's not so bad, but when you start talking about nonlinearities, it's a huge issue. I'll say something about that, but not too much. Now, what is the actual connection between solutions of these field equations and the twistor function? Okay, what is the connection? It's given.
You don't put any restriction on the positive energy solution.
I shall give that in a minute. Yes, okay. You're all leaping ahead of me. I'm going too slowly. That's clearly. Yes, you're leaping ahead of me. I shall say that in a minute. Yeah, absolutely. If you aren't interested in that for the moment, but are interested in the relationship between the field equations and the twistor function, what is the relationship? Well, it's a contour integral. What is the case? The simplest case is s equals 0. That is to say, you're looking at a scalar, and the field equation is simply the wave equation. The wave equation on phi. How do we get that connected with a homogeneity degree -2 twistor function? You just do a contour integral. Here is the twistor function. This delta z is this natural. It's this thing in terms of pi's. It's really it's differential, which differentiates out or integrates out the pi variables. You relate the pi to. You've looked at this is omegas and pi's in there. Wherever you see an omega, you put in the incidence relation. That makes it into a pi and an x. You integrate out the pi's. You're left with a function of x, and that is phi. That function of x automatically satisfies the wave equation. If this happens to be a higher spin thing, you have to make it homogeneity degree -2 to make it a proper contour integral. So you've got to multiply by a lot of pi's. If it's a negative degree, you bring it up to a -2 and then integrate out the thing as before, and you have a thing with these in. Each pi gives you an index, and so you have a solution of the wave equation automatically from the holomorphic nature of the f. If you have one which is positive or greater than -2 homogeneity, then you need to go by d by d. You notice this is the quantization rule in a sense, because here you have the pi's going to the complex conjugates. The complex conjugates are d by d omegas, and so you put d by d omegas in here, and then you get the unprimed indices. So you have the...
The x is now space-time coordinate then?
The which?
The x is a space-time coordinate?
The,
X.
oh, x is a space-time coordinate. Yes, I'm sorry. Yes. Yeah. X is a space-time coordinate. Geometrically, what does that mean? Well, let's take a particular case. Well, geometrically, what it means, first of all, is that x is a space-time point. In twistor space, in projective twistor space, it's a line. So a point is represented by a line here. A line, remember, is a Riemann sphere. Here is the Riemann sphere, which represents that line. The simplest representation of a function I can take here, I want a -2 homogeneity function. Let's take 1 over a product of two linear forms, linear expressions in Z. That's the simplest you can do. Where are the poles here? Where there are the two planes. I'm going to make these two planes intersect in the bottom half of twistor space, which we can do. That will give us a positive frequency function. That's the trick here. If you want a positive frequency function, and here's the more general case, make sure the singularities of our function f have two camel humps pointing up into the top half of twistor space, and it can do anything it likes in the bottom half.
But what the index of x mu, the Lorentz index of x mu, that for us is an index of a 4 vector, emerge from the index of omega and pi that are your...
I'm sorry, I missed something there. What the 4 vector?
Does the index x mu, you said that the x mu basically is the ratio between omega and pi, roughly speaking.
Oh, not x. X is a position point.
Yes. So is x sign is not the 4 vector.
X pi, yes, it's a 4 vector.
It's
Yeah.
a 4 vector.
Yeah.
So my question is, are the space-time index x mu emerge from the index of omega and pi? Because the index of omega and pi will be capital A.
It's the incidence relation. Let me go back to that. This is the relationship is precisely the incidence relation. Here it was. It's this equation here, or this one here. You see, the pi is there and the omega is there. What's that got to do with the space-time point? Well, it's given by the incidence relation here. So there, this is the x, is the r. And it contracts one of its indices onto the pi, and the remaining one becomes omega.
So it's like writing a vector using bispinor.
It is. Bispinors, it's a vector.
Now they're calling this in Italian, we call bispinor.
I don't know.
The R a bispinor?
Yeah, that is what I'm asking.
Yeah.
Is R-I-I
If you call that I think bispinor is something else, but never mind. It's got one index in the original spin space, the other index in the complex conjugate spin space. Yes. If that's what you mean by bispinor, yes, that's right. I mean, it's a Pauli matrix thing, and the connection with the twistors is that it contracts on the pi, and you get the omega, and that means that the x is incident with the twistor. So the geometry over here is that the x, you see, x is a line in twistor space, and the integral is done by converting. Well, I don't know how to say it. It's looking at x and seeing what the integral does on fixing the x, and then that gives us a relationship. For each x, I can eliminate the omega using incidence and then integrate out the pi, which amounts to doing an integral. What it amounts to is I'm taking my line here, which represents x. That's a particular Riemann sphere. I'm then taking the intersection with these planes, which gives us the poles. So there will be two singularities. I then do a contour integral between the two singularities, and that gives us a value. This is the value of the field at the point represented by x. It's the result of a contour integral. Is that clear? Yeah. Okay? So I have a very specific way of getting, this is in the scalar case, or when I've got the indices, doesn't make much difference to the geometry, it's doing this. Now that's in a special case. In a more general case, I might say I've got singularities which have two bumps up into the top half. I didn't say this before, it's related to your question, that if I take x in the top half of twistor space, that corresponds to a point in complex Minkowski space, which is what people refer to as the forward tube. And this means that if I just have two camel humps in the top, I can move that line all the way around in the top as long as I don't go into the bottom, and I'm going to have a positive frequency solution of the equations. So I have an honest wave function, which is not only automatically satisfies the field equations, it automatically is positive frequency at the same time. So it does a lot of things for you all at once. Okay, now that is a key thing. These are twistor wave functions of single particles. Now, there's something funny about this, which I worried about for a long time. I had the idea, yes, this top half of twistor space has got to be positive frequency. That was a big motivation right early on in the whole subject, to try and get positive frequency out of it. But here you have this very funny looking geometry with having to have these two humps up in the top. What does that mean? Well, it took a long time to understand that. If I'd paid attention when I was an undergraduate or graduate student to lectures that had been given at that time when people were talking about the theory of stacks, as they were then called, I think I might have understood. I certainly didn't understand it. Then, later on, I had conversations with Michael Atiyah, who made it clear what's going on. What is going on? Look at this picture. See, compare it with this one. Here I've got these two singularity regions. You see, the mistake is to think of the singularity regions, I think. The singularity regions have these two humps sticking up. What does that mean? Let's look at it in a different way. The top half of twistor space, that corresponds to the forward tube. It corresponds to positive frequency massless fields. Now, I can represent this top half as the union of two regions. I'm calling one U1 and the other one U2. One of them leaves out one camel hump, the other one leaves out the other camel hump. The whole space is the union of them. PT plus is the union of those two. PT plus, that means the top half. The function f is defined holomorphically on the intersection of these two regions. That is where I remove both humps. So I have a covering of the top half of twistor space by two open sets. The union of those two open sets is the region of interest. The intersection is the region where the function is defined. Now this is an instance of check cohomology, of first cohomology. You could have a much more complicated covering. I could have covered the top with lots and lots of regions if I wanted to, and then the algebra just gets a bit more complicated. But it is this, what I've written down in these colors, is the definition of a check one cycle. Is it one cycle? Yeah. Now you can represent that as a branched contour integral if you like, and that's what this picture is doing. It's more complicated than the simple contour integral I had before. Never mind, it doesn't matter too much. And don't worry too much about all these indices and all that, because I'm going to give you another way of looking at check cohomology, which at least in a simple case, because people who have never got used to these things find it all very baffling. It is a bit baffling, but it's a crucial point. And let me try and make it clearer by showing you this picture. This is a it's very nice to use this picture if you're going to try and explain cohomology to people who don't know any mathematics. It originated because I was being interviewed by some people for the BBC, I think it was, in some program, and I let slip at one moment. It was about twistors, and I let slip at one moment. Oh, it's really to do with sheaf cohomology. And they said, oh, what's that? What's that? So I said, no, I can't possibly explain that. You say, no, we'd like to know. So I came back the next day with this picture, you see. They didn't use it, I may say, but I was quite pleased with it nevertheless, because it's a very good representation of cohomology. And the cohomology here is the impossibility of this picture. See, that is a structure which you could imagine, at least part of it, you could make it out of a piece of wood if you wanted to, quite happily. In fact, I'm going to do that in a minute. I'm not actual wood. But, yeah, let me say what it is, you see. What I could do is I could construct my triangle like this out of, there's the triangle. And I want to know, see, I've gone to somebody, a workman, and he's produced these bits of wood here. And now there's some instructions about how I glue the pieces together. And those are the FIJs that I was talking about, you see. I could call, these are 3 open sets, and then I have, on the intersection, I have one rule which tells me how to patch this with this. I want to do that with that. And I want to know, is it going to be a structure realizable in ordinary Euclidean 3 space or not? Well, I have to work out the cohomology, and if the cohomology comes to 0, then I can do it. In this case, the cohomology doesn't come to 0, and the measure of the impossibility of this structure that I'm trying to build is this cohomology element. It is precisely that. It's precisely what you would get if you went through and did all the F's that I'm doing on here, and you check it's a cocycle, and it isn't actually, it doesn't have vanishing cohomology. Now, this is the case. You see, you find it. You try and fix it together, and you might fix these 3 points together, and you find the last one doesn't fit. And that is because of the non-vanishing of the cohomology element. Now, what does that mean, you see? It means that in twistor theory, I have my F's. It's not really an F's, you see. It's a cohomology element. The top half of twistor space is assigned this cohomology element. It's a sheaf cohomology element, as they call it. And that element is the wave function. Now, that wave function has automatically a non-locality when represented this way. It has, as I say, you see, twistor theory was aimed at trying to be non-local, but I had no idea it was going to come out this way. The non-locality that we get here is the information in the wave function. It's not made out of wood like this. These are holomorphic functions, and it's the kind of fact that they don't quite fit over the whole space, which is the first cohomology element. So what I'm saying, now I'm going to try and, see, I can't get quite to Bell. I tried to do this last night. I've been trying to do for many years. In fact, it's a problem I used to set my students. I say, okay, here's a representative, a clear representative of first cohomology. This is a prize. If anybody could give me a simple representation of second cohomology. Well, I sort of know how you do it, and I thought I might be able to bring you a picture this morning. I hadn't worked it out well enough to be able to do it. But I think I know a way you might do it. The sort of thing is that you imagine you go into a room, and this room has a spherical wall all around you, and you look around at this thing. It's got a mural painted on it, and you look at this thing and say, that's impossible. You look around, and then suddenly somebody opens a door somewhere in it, it makes a hole in it. Oh, now it's become possible. So can you think of something, a picture, which would be consistent over the whole wall, anywhere where you open a door and it becomes possible? Now, I think I can almost do it, but unfortunately, my pictures didn't quite work out. I have to work it a little bit longer. Good.
That's supposed to be that second cohomology thing's supposed to be connected more to Bell?
Yes. You see, as exactly the point that I think you were making a minute ago, this is one particle. Now, one particle is a non-locality, which is a non-locality that people have forgotten about, rather. I'm sure people used to worry about it in the early days of quantum mechanics. There is a non-locality for a single wave function. And here we have a single particle emitting a photon. Let's have a parabolic mirror or something like that. And here is the wave function here, and there's a screen at the back. Now, this screen is sensitive to the photon, and maybe it detects the photon here, or suppose it does. Then it's got the signal to everywhere else on the screen. It says, too late, I've seen it. Whereas somebody sitting over here, as far as the wave function is concerned, just locally there, how does it know that that wave function is not now representing a particle? That's a non-local feature. It also is a feature which cannot be represented without exceeding the speed of light. If it was like a water wave, and the intensity of that wave would tell you a probability of receiving the photon here, the intensity would tell you a probability of finding here, you might see them in both places. You might see them in neither place. That's not the way quantum mechanics works. The way quantum mechanics works is if you see it here, too late. You can't see it anywhere else. If it was a classical thing, you'd have to have a signal coming, bzz, 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 bzz. It can't get there in time because, after all, that's faster than the speed of light. So you already have a much more elementary non-locality in quantum mechanics. Okay, it's not got the subtleties of Bell anywhere near that kind of subtlety, but it's the kind of non-locality that it seems to me is reflected in the picture here. That's a first cohomology element. Now, you see, you would need a second cohomology element to represent two particles. If in Twistor theory you want a two-particle state, you have to take the product of Twistor, like we were worrying about with wave functions which belong to higher dimensional spaces. It's the product of Twistor space with itself, and then you've got second cohomology elements on that to represent two-particle states. Now, in that, somewhere, are the Bell inequalities, or if you like, the Bell inequalities are hiding, or the violation of them is hiding in that. There are ways that people do look at cohomology and try to represent Bell inequalities in terms, I think, Samson Abramovich and people have looked at these things. And I was trying to get a student to try and connect that stuff with this stuff, and he went off and did something else, unfortunately. I'm hoping that at some stage somebody will make more of a connection between the cohomology that we naturally get in Twistor theory, which will be a second cohomology element here, and to see how that relates to the chief cohomology things that other people have been doing to try and represent the violation of Bell inequalities, and when you can find a cross-section of something which gives you a realization, a locally realistic realization, and when you can't, and to try and connect that with the Twistor problem. Let me think of this slightly differently. You see, here we have this thing, that's the wave function zipping along and hitting the screen. And it is a non-local thing. If the impossibility in that thing is the information. Now, if somehow I tap off the information by looking at one point in the screen, the impossibility is gone. It is a non-local thing. If I observed it here instead, that part of the screen, the impossibility is gone. And so there's no information in the cohomology anymore. Now, what does it mean? This is when you make a measurement, you see. So you have to tie this in with what a measurement is. Now, how much time do I have, if any? None.
Well, I mean, you're almost full.
Can I spend 5 minutes or something?
Sure.
There is a very rapid part of the rest of this talk, which, you see, I think, and I've been trying to plug this idea for some while, as Diyoshi did and others, namely that the measurement issue has to do with gravity. Now, that would mean that it's when gravity comes in, when you have curved spaces come in, somehow the linearity which preserves this kind of impossibility will continue on. And it's the measurement which will introduce some kind of nonlinearity and so on. So I just want to give you two things here. First of all, how does Twistor theory address these questions? Well, it has been addressing these questions for a long time. These are old constructions. This is the Ward construction for self-dual Weyl fields, self-dual gauge fields, sorry. And what you do is you have your Twistor space at the bottom, and then you put a bundle over it, and you patch it together, and you find you get first cohomology elements to describe the structure of the bundle. And indeed, it works, but only for the left-handed fields, which is kind of curious. This was slightly, I had an earlier construction, which was to do with piecing together twistor spaces to produce gravitational fields. And you can do that, works fine, but only for left-handed fields. So you can make complex solutions of the Einstein vacuum equations which are left-handed. That is to say, the right-handed part of the Weyl curvature vanishes, which means it describes in a certain sense, it's what I used to call the nonlinear graviton. This is a left-handed nonlinear graviton. Now, it's been a huge obstruction to the development of twistor theory, in my view, the biggest obstacle to taking the theory seriously as how you describe the world in terms of twistors, which is that this never seemed to work for the right-handed fields. This is what I call the Googly Problem, and only people who belong to the former British Empire will know what a googly is, I suppose, because it's a cricket ball bowled so as to look as though it spins left-handed, whereas it actually spins right-handed. So it's a very difficult thing to do, but nevertheless, it very much expresses what I'm trying to do here. That is to say, using the formalism which naturally bowls you right-handed massless particles and make it bowl you a left-handed one. And that's what we call the Googly Problem. Now, I should say the Googly Problem is about, 40 years old. It's been obstructing the development of twistor theory for all this time. And, that's been to my view, it's been the biggest problem in twistor theory. Now, there is a development which is about a year old, which I haven't been able to work my way through yet, which is to try and do something a bit more subtle than this. See, this is taking pieces of twistor space and gluing them together and make a curved twistor space. But what I'm going to do now, this arose out of some conversations or one specific conversation with Michael Attia particularly, is how to generalize that in a certain way where you're trying to patch together the spaces without knowing what the spaces are. And that required not looking just at the complex, the holomorphic functions on the space, but to looking at the algebra, the sort of Heisenberg algebra. That is to say, you look just at not just at the functions of twistors, but look at the differential operators as well. So it has built into it the twistor quantization rule. So, although I don't really know how to do this yet, it is something where you bring in the dual twistors. See, once you bring in the dual twistors, you spoil the whole thing because it's not holomorphic anymore. You want to keep things holomorphic if you can. But the trick is not to bring in the complex conjugate, but to bring in the differential operator d by dz instead. It doesn't commute with z, so now you have a non-commutative algebra, so that instead of having the holomorphic functions, you have this algebra which is non-commutative. And then you go through all the things we were talking about before and patching things together, and now it should be ambidextrous in the sense that you have right-handed and left-handed, both in the same formalism. Now this is, I think, along these lines is going to be the solution of the Googly problem. It's not worked out yet. I just have hopes that this is how it's going to work. One other comment, if I could make that. It's a whole really other topic, but I think I should just explain where I go from here with regard to the measurement issue, since that's a big thing in the discussions that we've been hearing about here. I don't have a solution to any of these things. I think that twistor theory is probably the way to go because it's got natural non-localities in it, and that it may ultimately form a framework where one can formulate physics in a way which is non-local in the right kind of way. So that's the hope. Now it has to bring in aspects of general relativity, which needs to solve the Googly problem in the sort of ways I've been saying there. That's something for the future, no doubt. But nevertheless, I also would hope that it will give us something ultimately which deviates from standard quantum mechanics. Now, the principle that I'm just going to hint at in a minute, which I think standard quantum mechanics has problems with, is the Galilei-Einstein principle of equivalence. The principle of equivalence, of course, says that a gravitational field is equivalent to acceleration locally, or here we have an imitation of Galileo dropping a big rock and a little rock from the top of the Leaning Tower. Whether he did or not actually is not the point. And an insect sitting on the big rock will look at the little rock as though there was no gravity. And of course that's experienced by space travelers and so on. Now, does that make sense in relation to quantum mechanics? And I want to say there is a problem here. Now, the problem can be illustrated this way. Suppose we have a tabletop, we're trying to do a tabletop experiment. And on the tabletop, we are trying to do quantum mechanics, just a simple little problem where we have a gravitational field to take into consideration. Now, we might do this in two ways. One would be two alternative ways. One is the Newtonian, which would be the sort of conventional physicist way, which would say, oh, well, we just put in a potential for the Newtonian field and proceed as though it was ordinary quantum mechanics. No problem. Except that that's not the way Einstein tells us to look at a gravitational field. Einstein says instead we should think of the gravitational field as an acceleration. So we imagine we take a frame of reference which drops freely. These are the purple coordinates now. In the purple coordinates, we drop freely. There is now no gravitational field. We then transform back to see how it compares with the other wave function. And what you find, perhaps not too surprisingly, is there is a phase factor which relates the two wave functions. So the green one is the Newtonian wave function, the purple one is the Einsteinian wave function, and here we find a phase factor which relates the two. In fact, there are old experiments. Colilla, Alberthausen, and Werner did some experiments to show that the principle of equivalence, if you like, was consistent with quantum mechanics. And you might say, phase factor, who cares? These are equivalent physics. They're not. Because, look here, you see there's a t cubed in the factor. What does that do for us? Well, if you're staying in one gravitational field, not much. You can choose. What it's telling you is that the two are different vacua. They are different, belong to different Hilbert spaces. You are treating physics according to different vacuum. It is actually the same thing as Unruh, the Unruh effect. The Unruh effect is to tell you that if you are in an accelerating frame, you feel a temperature, which is the same thing as the Hawking radiation. If you have a black hole sitting there and you hold something above the black hole, it feels a temperature, and this can be thought of as the Hawking temperature or as the Unruh temperature, that the acceleration of that particle, what it feels, because it's not dropping freely. If it drops freely, it doesn't feel the Unruh temperature, and that temperature then is only felt if by stationary fields outside the hole. Okay, you've got different vacuum. In the case of the Unruh effect, it's a thermal vacuum. But if you look at the temperature of that, you find it has the speed of light squared or something in the bottom, which tells you that if you imagine the limit when the speed of light goes to infinity, which is what I'm doing here, I'm considering the Galilean limit or the Newtonian limit, the speed of light's gone to infinity, and you then have no temperature anymore. But it is still a different vacuum because of this phase factor here, which involves a t cubed. Now, that's probably not a problem if you're just going to do an experiment with a constant gravitational field. But suppose you have an experiment in which you have an object which is supposed to be in a superposition of two different locations. Now, those two different locations, each will have its own gravitational field, and therefore, if you're sitting over here, you will feel two different accelerations which are in superposition. And this is telling you that you have to be doing your quantum mechanics in the same Hilbert space, or else you're in trouble. But you're not in the same Hilbert space. If you look at the Einsteinian point of view, you've got different Hilbert spaces. So what do? Well, I don't know what you do in general, but at least I can say I can measure an estimate of the error. And that is, how far wrong am I going? So I take the difference in these g's, it's the troublesome term here, and I square that and integrate it over space. This is a quantity I'm calling Eg. It's equivalent to, by doing just a little bit of manipulation, to the gravitational self-energy of the difference between these mass distributions. So you take this one and subtract it from that one, work out the gravitational self-energy of that difference. That is a thing called Eg, which is the same as the error term in what I said before. which I'm claiming is a problem. Now, the way I'm interpreting this is to say that it is the way nature resolves this problem is, in a sense, to invoke the Heisenberg time-energy uncertainty. And as one would do with an unstable particle, you say there is an energy uncertainty, and that's reciprocally related to the lifetime. So what I'm saying is that there is a time scale for the survival of that superposition, which is you integrate the mass distribution of one, subtract it from the other. I'm sorry, you subtract one mass distribution from the other, you square that. What am I saying? You subtract one mass distribution from the other, work out the gravitational self-energy of that. That is the energy uncertainty of that system, which I claim is reciprocally related to a decay time. It also can be reinterpreted in this sort of way, which is, I think, a bit like something that Giancarlo was saying just a minute ago. See, here we have a lump of material. It gets put into a superposition of two locations. You look at the way the difference between these two geometries, and there's a certain region where the difference of these two geometries, you work it out, and you see when this reaches a sort of Planck scale of unity, then you say that's a critical point where something happens, and it has to make a choice between 1, 2, and nature goes one way or the other. And that is the state reduction process. And you can see in general qualitative terms that this happens when the deviation between these spacetimes, in an appropriate sense, reaches a Planck scale. And that is when one thing or the other happens, according to this view. And that would be coming about when you try to combine quantum mechanics with general relativity in a way which respects the principles of general relativity. And this is just to show that there are experiments which are still under, well, Dirk Baumeister is really the person in charge of these, who's been working on them for over a decade now. When I saw him about 3 years ago in Leiden, quite uncharacteristically, he said to me, in 10 years, we'll have an answer. That is to say, does this proposal I just mentioned, which is similar to Dioshi's earlier proposal, does this proposal, is it respected by nature or is it not? And I saw him again 2 years later, wondering if 10 years was a constant of nature. And he, quite uncharacteristically, I thought, with no prompting, said, in 7 or 8 years we will have an answer. So I thought that was pretty consistent. That was a year ago, so I suppose it's 6 or 7 years from now. So I'm keeping my fingers crossed. Thank you very much.